board. We saw that last time. Okay. So if we know the Ka for acetic acid, we can calculate the Kb for acetate ion. So Kb is going to be equal to Ka over K, oh, sorry, Kw over Ka, which is 1 times 10 to the minus 14 over 1.7 times 10 to the minus 5. And we'll get 5.6 times 10 to the minus 10. I'm showing you this here because eventually when we calculate the pH, for instance, if we calculate the pH of sodium acetate with a certain concentration, we would need to know the Kb value because that's the equilibrium that's going to matter. Whenever we're dealing with a salt, you almost always have to convert between Ka and Kb, so pay attention to what's showing up on the reactant side. You have the conjugate base of the weak acid. You need to make sure you're using the Kb. Does that make sense? Questions about any of that? Yes?
Will our Kw always be the 1 times 10 to the negative 14?
Yeah, I think at this point we're just going to be able to assume that that's the Kw we're working with. We asked the one question on the exam, what's the pH at a different temperature, and we give you a different Kw. I think we're done with that now.
Okay.
Yeah, so Kw is going to be 1 times 10 to the minus 14. Yeah?
Does this only work for conjugate acid?
The Kw equals K times Kb? Yes. So that is only true for conjugate acid-base pairs. So the Ka of acetic acid and the Kb of acetate ion. And those are the ones that are related through the Kw. Yeah. Other questions? Okay. So we're talking about putting sodium acetate into solution. We look now at the acetate. Now we need to consider the sodium. And we have here a salt whose cation has neutral properties, such as sodium ion, and whose anion is the conjugate base of the weak acid. The solution is going to be basic. So essentially, sodium is not going to contribute to the overall pH of the solution. And we can write out the reasoning why, sort of following the plan that I like to use, which is taking our ion, adding water, and determining if the resulting product could form. So if we have now a cation, like sodium, it could be potassium. Okay, that's another common one. Maybe magnesium, maybe calcium. Those are not going to be as likely. We're going to add, we're going to take our cation, we're going to add water, and we're going to see what we can form. The two things that we could possibly add to the sodium ion are H plus or OH minus, and you can't have a positive plus a positive. So we're going to have the possibility of forming NaOH and H plus. And we know that that is a strong base, so this reaction doesn't happen, just like with the strong acid. I know this part is really confusing, so please ask questions now if you have them. What I'm doing now is trying to see what I could possibly form by adding water to the sodium cation. The only possibility would be sodium hydroxide, because we can only add OH minus to that sodium from water. And because we know that sodium hydroxide is a strong base is completely dissociated in water, that's not going to form that product. Does that make sense? So for our sodium acetate, NaC2H3O2, we end up with a basic solution. because the acetate C2H3O2 minus forms OH minus in solution, and HC2H3O2, acetic acid. Okay, that's the equilibrium. Yes.
You can explain how the above equation relates to the top sentence?
It doesn't exactly. It doesn't exactly. So what the top sentence is saying is that when we look at sodium acetate, it's got a neutral cation. So that this equation is showing you that it's a neutral cation because it can't form a product that is actually feasible. And because the anion that we just talked about in the previous slide was acetate, that can form OH minus. That's how we end up with the basic solution.
Would it also not work if you had like a strong acid product, since that would also completely switch?
Exactly, yeah. So when we looked at the very first example last time, so, we had chloride ion. We added the chloride ion in water. The only possible conjugate of that is HCl, which is a strong acid. Does not have a neutral solution. Other things. Okay, so if we then have in solution the conjugate acid of a weak base, we're going to make an acidic solution. So here's an example of ammonium chloride. Ammonium chloride, and this is one where you're going to have to make sure you know how this is going to dissociate as the salt. So we're going to form ammonium ion and chloride ion. Okay. Will chloride ion affect the pH of the solution? No. Okay. It is the conjugate base of a strong acid. So it will not affect the pH of the solution. Okay. NH4 plus ammonium ion, yes, it will affect the pH of the solution. So why don't you take a few seconds, try to write out the reaction of NH4 plus and water, predict the products, and let's see what the pH, well, it's kind of given. It's going to make an acidic solution, so make sure you end up with an acidic solution. But try to write out that equation, chemical equation. Okay, so when we put ammonium into water, okay. Oh, forgot my plus. Now what we can have happen is that a proton from ammonium can be added to the H2O. So it can be donated from the NH4 plus to the H2O to form H3O plus. And we're left with NH3. Okay, so ammonia, NH3, is the conjugate base of ammonium ion. Okay. How hard is that to recognize? Truly ask, like, is that? Okay. All right. So here you can see on our product side, we have H3O plus. This equilibrium can happen, right? So we have to end up with an acidic solution. Yes?
How do you know when H2O is the donor versus the acceptor?
Yeah, that's the tricky part. Thank you. Yes. So I think it's easy to recognize with a cation, except for this one. So ammonia is kind of special. Ammonium is kind of special. But if we have a cation that is a group 1 or 2, sodium, potassium, magnesium, calcium, okay, we can easily imagine adding OH minus to that, right? And possibly forming whatever hydroxide. With this, let's see. I guess one way to think about it is we have two options with ammonium. One option is to add another proton, to have NH4 2 plus. And the other thing is to take one away. Okay? And to have NH3. So you've probably never seen NH4 2 plus, NH5 2 plus. Because that doesn't exist as far as I know, unless there's some like weird phase that could possibly exist in. For our purposes, it does not exist. And so that's one way to address that situation. This is a lot of practice. I'm going to be very honest with you. It's a lot of practicing these problems and figuring out what could possibly form. Is that at all helpful? I mean, it's probably not the answer you want.
It's okay.
Other questions? When you have an anion, it's also easy to imagine adding an H plus, but you can't add an OH minus. So when you have those charges, it sometimes helps. This is a case where it doesn't. Okay. All right, so we did this. We wrote out the equilibrium expression for ammonium ion and water. The Ka for this, based on our last slide, is going to be concentration of the conjugate base, which is NH3 times H3O plus over concentration of NH4 plus. Okay. We won't find a Ka for NH4 plus, most likely on a table, but we will find the Kb for NH3, and it's 1.8 times 10 to the minus 5. So calculating the Ka for NH4 plus, take our Kw divided by the Kb, and we end up with 5.6 times 10 to the minus 10, which is only coincidental with the previous problem. They don't always end up being the same value, okay? When we did acetate, we ended up with a Kb because it's the same number as this. It's just a coincidence. Okay. All right, so the summary is that if you have a salt with an anion with neutral properties, such as chloride, and whose cation is the conjugate acid of a weak base, the solution will be acidic. So if we have a conjugate acid of a weak base, we have an acidic solution. I think it makes sense to practice these. Here is an example where we have ammonium acetate. We put this into solution and we get ammonium ion and acetate ion. Both of these can affect the pH of the solution. Okay. I don't think that no, I know that this will not be on your exam. So we're going to skip over it. I still think it's like really interesting and helpful when we figure out like for all this kind of practice. Down to is you look at the Kas and the Kbs, predictions by comparing those. So this is only if you have two ions, a cation and an anion that can affect the pH of the solution, and you can look at the extent to which both will ionize and make comparisons. It's really cool, but we're skipping over it. Your book does a terrible job of explaining it anyways, so congratulations, or I'm sorry. All right. Okay, so let's take a look at these four. I'm going to have you work on these with your neighbor. Are we going to end up with a solution that's acidic, basic, or neutral for each of these four solutions? And then I think we have a number of these that we'll actually do demos for. So go ahead and try these. Give you a couple minutes. All right, let's take a look at this first example. We have NH4NO3, so ammonium nitrate. When we put ammonium nitrate salt into solution, it's going to dissolve into ammonium ion and nitrate ion, NH4 plus and NO3 minus. Okay, so for this first example, I'll walk you through what we're going to do. We're going to take each of these ions and combine it with water and determine what the products are. We saw the ammonium example just a couple slides ago. If we take ammonium ion, combine it with water, we're going to get H3O plus and NH3, ammonia. And because we end up with a weak base and H3O plus, we know that this reaction can happen. It's going to form, that's going to end up with an acid, an acidic solution. What about for nitrate? Yeah, so one of the yes, sorry.
Do you want me to answer it?
Sure, yeah.
Or at least what I think it is that it will form nitric acid and OH minus, and since nitric acid is a strong acid reaction.
Exactly. So if we take NO3 minus, combine it with water, the possibilities for products are HNO3 and OH minus, and HNO3, nitric acid, is a strong acid. So that reaction will not occur. Okay, so NO3 minus is the conjugate base of a strong acid. This reaction doesn't happen, and so this equilibrium doesn't exist, will not affect the pH of the solution. So when we put ammonium nitrate into solution, we should end up with an acidic solution, right? Everyone agree? So we have H3O plus as our product. So I have ammonium nitrate. I can't see that well, but I can only see this. So let's see here. All right, so we've got a number of beakers here. These all contain an indicator that changes color with acidic basic. We have reference, this is an acidic solution, it's a red color, and our basic solution is blue. We're going to have a neutral reference, so these beakers are all neutral, and to these I'm going to add different salts. So, first one, we just did ammonium nitrate, we said it should be acidic. I guess we should kind of expect that red to orange to yellow is all going to be acidic. Okay. Cool. Perfect. Yellowish. Okay. What about sodium fluoride? What did we end up predicting for that? Basic? Everyone agree? Alright. So it should end up somewhere in the green to blue range then. Sodium fluoride. Oh, yeah. Okay, cool. So let's write out the reasoning why. Okay, so that was sodium fluoride. So if we take our sodium ion, combine it with water, we could possibly form sodium hydroxide and H+. But we know that sodium hydroxide is a strong base, so this reaction can't happen. If we take our fluoride ion, put it in water, we could possibly form HF and OH minus. And what do we know about HF? It's a weak acid. It's not on the strong acid list, so it is a possibility here. Okay? We end up with OH minus in that equilibrium, meaning we should form a base, and that's what we saw with our indicator. Questions on that? All right. KCl, potassium ion, chloride ion, these are conjugates of strong bases and acids respectively. So if we combined K plus with water, we could potentially form KOH, which is a strong base. And we could potentially form HCl if we combine Cl minus with water, and that's a strong acid. Okay. So those won't form. We should end up with a neutral solution. That'll be the same for sodium chloride as well. Okay, so we'll prove the concept of that. Here's some sodium chloride. Nothing should happen. Ta-da. Okay. We have one more example. Sodium carbonate. Okay, we know what's going to happen with sodium, hopefully. Na plus, I'll go ahead and write it out, plus H2O could potentially form sodium hydroxide plus H plus. Sodium hydroxide strong base, doesn't happen. So then with carbonate, okay, what's the possible product here? HCO3 minus. So we're only going to add one proton. So this is the conjugate acid of CO3 minus. And OH minus is the other product. So this should make a basic solution. Right? Yes?
Just ignore the fact that it's 2 NA plus, it'll give you the same result if you take a credit again.
So, sorry.
The fact that it's 2 NA plus, you can just
Oh.
ignore that.
Yeah, so because it's 2 Na, you only really need to consider the fact that it's 1. That reaction would be the same. If it was if you wanted to leave the 2 in, you would add 2's everywhere. It's all going to be the same. Okay, so let's try our sodium carbonate. I don't know the answer to this, but do we think it's going to be more or less basic than the sodium chloride? We could look it up. We could figure out some KPs. We don't need to. That's not as fun. That's pretty nice. So would the sodium carbonate, do you think, be more or less basic than the sodium chloride? More basic, yeah, closer to the blue. Not even be dark. Pretty. All right. What do we have left? Oh, we have 2 good ones left. This sodium compound and then our iron compound, right? So when we put this in solution, we get sodium ion and HSO4 minus. Okay? Don't try to dissociate that any further. All right? So we need to consider how this could affect the pH. What do we think? Yeah, take a look at that one. Make a prediction on if you think it's going to make an acidic or basic solution. It will make either one here. It's not going to be neutral. And then we're going to do the experiment. I guess let me do it this way. With HSO4, we could plus or H3O plus triangle. Or you could add a proton and have H2SO4. Right? Because we know both of those exist. Okay. Is this possible? No, why not? Strong acid. But this has to do what happens. This will not form. This is a strong acid. We dissociate back into that. Okay? Let's make sure we form an acidic solution when we put this solvent into the solution. Sodium bisulfate, here we go. Okay, all right. This is probably other than our Lewis acid, which is going to happen here too. This is the hardest example. Okay. What about for our iron? So this is going to be completely dissolved. We're going to form nitrate ion, which we know won't affect the pH. We saw an example with nitrate ion. HNO3 is a strong acid. We need to consider iron 3 plus. Remember these? Does iron act as a Lewis acid or a Lewis base? Do we just do it and try it? Let's try it. Okay. All right, so here's our iron. So we made an acidic solution. What's that reaction? What's formed, do we know? I'm going to leave it because we're not going to throw any Lewis acids and bases at you, really. It is possible, but I don't. I'm going to leave this one, okay, because I want to keep going. I have a couple slides here that I'm going to fill in later so that you can see those. Now I want to do an actual calculation. So we want to figure out the pH of the solution where we put 0.1 mole of our sodium fluoride in 500 milliliters of water. Okay? And we're given the Ka for HF. And we recall we have our sodium fluoride. It forms this basic solution, so we need to end up with a basic pH. Okay? So let's look at how we're going to solve this. I always start out by reminding myself what I'm doing. Okay, so if I take sodium fluoride and put it in solution, I'm going to form sodium ion and fluoride ion. Okay, I write this out specifically just to keep track of everything. I know, after having done many of these problems, that sodium is not going to affect the pH of the solution. It is the conjugate acid of a strong base, meaning it won't react with water. Fluoride ion, though, as we've seen today, can react with water to form HF and OH minus. Okay. Based on that, this equilibrium, we know we should form a basic solution. If you can get to this point, you've done at least a quarter of the problem. The rest is math that you've already done before. Okay? This is a big step. And I'm not just saying that. I know it's two equilibria, or one equilibrium and one reaction, but there's a lot of work that goes into this part. From here, we're going to use an ice table. We've got equilibrium. Okay? Solve the problem just like we will any other equilibrium problem. Concentration needs to go in the ice table, and we need to make sure that we're using the right K value. And we almost always give you the opposite one, just because this is how we typically see these values in tables. We typically wouldn't see a table of conjugate bases and have their KBs. We would see the acids, weak acids, and have their KAs. And so that's what we've given you. For HF, our Ka is 7.2 times 10 to the minus 4. Okay. The other annoying thing in this problem is we've given you 0.1 moles in 500 milliliters, or 0.5 liters. And so that is equal to 0.2 moles per liter. Okay. Now that's 0.2 moles per liter of sodium fluoride. Moles per liter of NaF. We know, based on the formula, that for every 1 mole of NaF, you get 1 mole of F minus. Okay, this is me being incredibly detailed in my work. I don't know that I would necessarily expect you to do that, but pay attention to the formula, okay? Because we may see, there's 2 sodium here, that kind of thing. You may need to double some things. So anyway, we end up with 0.2 moles per liter of F minus in solution. Okay. All right. So I'm just rewriting that because my dimensional analysis got in the way. So we're going to do an ice table, like I said. 0.2 moles per liter to start with F minus. We're not going to worry about water, it's pure liquid. We're starting with 0 moles per liter of products. There is no HF in solution initially. We're only putting in sodium fluoride and no initial moles per liter of hydroxide. So just as we would previously, we're going to do minus some value x of F minus, plus x for HF, and plus x for OH minus. So then at equilibrium, we're going to have 0.2 minus x for F minus, x moles per liter for HF, and x moles per liter for OH minus. Because we're using F minus, the conjugate base, we need to use the Kb value for this equilibrium constant expression. Okay. Kb is going to be equal to the Kw divided by the Ka, 7.2 times 10 to the minus 4. And that value is 1.4 times 10 to the minus 11. We're going to have that equal to concentration of products at equilibrium, x times x, or x squared, divided by concentration of reactants at equilibrium, 0.2 minus x. Okay. Y'all remember from last week making the assumption that x is small relative to the initial concentration? Yeah. So we can take the initial concentration of F minus divided by, this case, the Kb. And if that's greater than 1,000, we can ignore that x. And then that will be the case here. You can also kind of tell because KB is so small, times 10 to the minus 11. Okay. And 0.2 is like times 10 to the minus 1. So we're going to get rid of that x. Moral of the story. Do check your assumptions, though. Okay, so then we solve for x. Oops. So we'll multiply both sides by 0.2 and then take the square root. And we're going to get x is equal to 1.7 times 10 to the minus 6 moles per liter. Okay. The question asked us for pH. X is equal to the concentration of OH minus, all right? Because X is OH minus in our equilibrium line. And so we can either convert to concentration of H plus using Kw equals concentration of OH minus times concentration of H3O plus, or we can convert to POH and then do pH equals 14 minus POH. Either one, but you do have to get pH, not POH. So that's an easy place to make a mistake. And I did it this way. I did POH equals 5.78, and so pH is equal to 8.22 from that equation. And it's basic. That's good. Not super basic, which actually makes sense with our indicator. Okay, before we pack up, 2 things, maybe more. With these problems, the easy places to make mistakes, like super easy, not converting between Ka and Kb where appropriate, and then calculating either pH or POH and getting the wrong one, okay? So those are just simple things. Everything else is an ice table, all right? We'll see you next time.